Yeah, teachers that you haven't seen before. Yeah. Yeah. Oh, that's normal. That's normal. Okay, so let's see. We have no homework to do, which is great, so we can go straight in now. Atoms, and we are at photons. Okay, great. Right, photons. Have you done photons in chemistry?
No, photons, no.
You will shortly. Are you doing the quantization, quantum in chemistry?
No, doing rate filtration.
Doing what?
Rate of
Reaction rate.
Yeah, reaction rate.
We did that in maths. Okay, photons. Yeah. You got this? Yeah? Okay, photons. So, there's a lot, but it's not as much as you might think. So, we have to first define some terms. A quantum is a word you heard before, maybe, or quanta for plural, I believe, is the minimum amount of any physical entity involved in an interaction. So for, I suppose a simple example might be like in football, the smallest score you can have is 1 goal, or what else would be relevant? It's the smallest unit you can use for a measurement, and it's not possible to have less than this unit. So can you have half a goal, football goal? No, you can't score half a goal, can you? You can only score 1 goal, 2 goals, or 3 goals. So a quantum is the smallest measurement that you can make, and the measurement smaller than this doesn't have any meaning. It's not possible. So usually you can make a smaller measurement. Like, is there something smaller than a centimeter? Yeah, what's smaller than a centimeter? A millimeter. Is there something smaller than a millimeter?
Yes.
Yeah, a micrometer. Is there something smaller than a micrometer? Nanometer, and so on. Okay, you got this?
Should I go?
Yes. Has everyone else got this? I'm not going to wait for you, Karai. You'll have to get it from someone. So far, we have no need for quanta. For example, we don't have quanta of distance. Like I was saying, if you have a meter, you can have a centimeter. If you have a centimeter, you can have a millimeter. If you have a millimeter, you can have a micro and a nano, and so on. So distance can be any number. 10 to the minus 10, whatever. 10 to the minus 11, 10 to the minus 12, whatever. Now, a photon is a single quantum of light, and it's referred to as a light quantum. So we'll explain what that means. Okay. So, like I was saying, if you have 1 meter, you can have less than 1 meter, and so on. This is not the case with light, and this is something that you'll learn in chemistry as well. With light, you can have less light and less light and less light, but there is a minimum amount of light you must have, and you cannot have less than this amount. This is called a photon. It's the smallest amount of light that you can have. So what I mean by that is, imagine that you have a light bulb, and you turn the light on, and then turn it off really quickly. You see what I'm saying? So it goes on and then off really quick. So you get a little bit of light, yes? Now if you turn it on and turn it off quicker, you get less light, a smaller flash of light. Do you understand? The question is, can you turn it off and then on and then off quick enough to keep reducing the light? And you can up until a certain point. At some point when you turn it on, and if you turn it off quick enough, you turn it off so quick there's not enough time to make at least one photon of light, that there is a minimum amount of light that has to come out. Otherwise, no light comes out. Do you understand? Yeah. So this is a photon. It's the minimum amount. It's also called a quantum of light, but we shall call it a photon. You got that? Yeah, let me try and fix the colour temporarily. Okay. Now, we should think of light as a group of photons. So when the light comes out of the light bulb, we should think of it as many, many photons, because photon is the smallest amount. Okay. Next now. Right, so some distance, a smaller distance, an even smaller distance, an even smaller distance, an even smaller distance, an even smaller distance, etc. No smallest. I'm making this point again. Some light wave, a smaller light wave, an even smaller light wave, and so on. But there is a smallest light wave, and this is a photon. Okay, so again, I'm just repeating myself. Are we clear on what a photon is? Yeah. And then we have no light wave. Thus, a photon of light is like an atom of light. Do you get the analogy? That, you know, in chemistry you have atoms as the smallest part. Photons are like the smallest part of light.
Photon is, atom is a photon.
No. I'm saying a photon is like an atom of light, the smallest part of light.
But the atom
Yeah.
is the smallest thing.
Yeah.
A photon is still the smallest thing of the material, of anything.
Yeah, but light's not a material, so it's the smallest.
Anything.
Photon is the smallest part of light.
Only light?
Only light, yes. Yeah. Yes. No, I understand. So in general English we call quantum the smallest part of anything, but photon is the smallest part of light.
Only light.
Only light, yeah. Okay, so a photon is a particle of light as well. That is a single quanta of light. So we think also of a photon as being like a particle, a light particle. Do you get what I'm saying? That I know light is a wave, but we can think of a photon as a piece, a particle. Yeah. Okay. Einstein, or Einie, as he's known to KJ, discovered that energy of a light photon or other radiation, electromagnetic radiation, not just light, you know, X-ray, radio, whatever. He discovered that it only depends on the frequency of the light. Now, I want you to kind of appreciate why that is rather unusual. If you had an ocean wave hitting a boat, for example, can you picture there's a boat in a storm and there's an ocean wave hitting it? There's two things that are important about a wave. The wavelength, which is how long the wave, well, there's three things. The wavelength, which is how long the wave is. What's this one called? The height of the wave. The amplitude. And then how fast the wave is moving is the frequency. So when you think about the energy from the wave when it hits the boat, what is the most important thing for the boat? You would like to know how fast the wave is moving, so that's the wavelength. But also, what else is important? The amplitude, how big the wave is. What Einstein discovered, which is rather odd, that for light and light energy, it's not important the amplitude is not important, that the energy is determined only by the frequency, not by the amplitude. And that is kind of strange, because that's like me saying, when the ocean wave hits the boat, you only care about the wavelength and the frequency. You do not care about how big the wave is. Now, if you're on a boat and the wave's hitting you, you would care about how big the wave is, because a bigger wave would be more energy hitting the boat. But for light, it's odd that it's only the frequency and the wavelength and not the amplitude that counts for its energy. Do you understand why that's unusual? Yeah. So Einstein discovered this, that the energy of light depends only on the frequency of light. Now, it also depends on the wavelength, but that's only because, if you remember your formula, do you remember from semester 1 that V equals lambda F? And what's the speed of light? C. So if you know F, it's the same as knowing lambda. You know, that it's really, you know, if you have the F, you have the lambda, and vice versa. So when I say depends only on the frequency, that also means depends only on the wavelength. Anyways, that is, the higher the frequency, the more energy. Now, there's a formula here that you can calculate the energy of a photon of light if you know its frequency. In fact, it's a very simple formula. It's just the frequency multiplied by this constant known as Planck's constant. And this constant you will study in chemistry, and its value is given there, 6.62 times 10 to the minus 34 joule seconds. This formula you will do with Lorraine. She doesn't usually use F for frequency. In chemistry you use a kind of V symbol. In chemistry you use a V, well it's actually called a mu or something. And it's a Greek letter. You got that?
Yeah.
Yeah?
Which one minus what?
34 kJ. Okay, you have that? But in fact, this is not really a new result. Although it was discovered 100 years ago, this formula, it was known before this. If the frequency is higher, that means more energy. What colour of light has the most frequency?
Right.
No.
Blue. Indigo.
Blue, violet colour, indigo, yeah. Red has the lowest frequency, so it has the least energy. I don't know, about maybe 150 years ago, maybe 200 years ago, this result was discovered by accident. That if you have you remember the prism, the triangle glass, and the light comes into the prism, and then what do you get on the other side? So you have all the different colours. If you line the thermometers up so that the rainbow of colours hits a different thermometer, the red hits one thermometer and the green hits another thermometer, the one at the end, the violet colour, will be slightly warmer than the thermometer that was receiving the red light. Yeah, so this isn't actually, it's a result that's been known for some time, but not maybe the reason why. So the reason is higher frequency means more energy from this formula. Okay? Now, here's an example question. A photon of red light has this wavelength. What is its frequency? How much energy does it have? How much energy does this have in electron volts? Now this is a question you should be able to do, because I just gave you the formula right there for energy and the constant. Okay? So I want you to try this for me. First calculate the frequency. What formula do you need to use to get that? See? What formula? You don't remember because you're not revising. What formula do you need to use? And I wrote it on the board in this class. What is it?
Lambda. C equals lambda.
C equals lambda F, yeah. do it now. So the wavelength equals 400 nanometers. So you have C equals F lambda. So F equals C over lambda, which is 3 times 10 to the 8 meters per second over 400 times 10 to the minus 9. So here the frequency is 7.5 times 10 to the 14 hertz. Part B is what is the energy. So the energy equals the frequency times Planck's constant. So that would be H multiplied by F. Oh, come on, Pad. Come on, you can do it. One moment. My pad is temporarily dead. I'll have to write in with the pen. So this equals H multiplied by F. Now you have the F from here. What's the value of H? 6.626 times 10 to the power of minus 34. So when you multiply that out, you get a very small number, as you should. Here's back. 4.97 times 10 to the minus 19 joules. Now because that is so small, we usually convert it into electron volts. So if I convert this into electron volts,
minus 19.
that's what I got. No? Minus 19?
What did you get for the
10 to the 14.
10 to the 14?
Yeah. So converting this into electron volts, you get 3.1 electron volts. Very straightforward calculation. But you've all forgot, most of you forgot the formulas that you need here from semester 1. Right, next now. So here's another one. You have your mobile phone, and this mobile phone operates at about 900 megahertz. So there's a wave, listen, there's a wave coming out here of 900 megahertz coming out from my phone, connecting to the phone tower. Yeah. The power of the phone is about 4 watts. So my question is, per second, how many photons of light are coming out? So you know the frequency, you know the power, you know what's the formula for power? It's W over T. So this is per second, so what's the T? 1. So what's power? The same as energy. So you know that the power per second is 4 joules. You know what the frequency is. So you can work out the energy for 1 photon and then divide it to work out how many photons you have. So I'll do this one now. We'll have a look at the picture. So what you have is you have your phone, and there's lots of photons coming out. And each of these photons are little waves of light coming out from the phone. The work, or the energy, is 4 joules. The energy of 1 photon will be HF. What's the F here? I said it was 800 mega. Thank you. 900 mega. What was our Planck constant? 6.6?
2 times 10 power minus 34.
Thank you. So if I multiply this by 900 mega, I get the energy is 5.96 or 958 times 10 to the minus 25 joules. Now, that's the energy for one of these photons, but in total you have 4 joules of energy. So you want to know how many of these photons must you have to make 4 joules. So it'll be a lot, as it should be, because each one is so small. That's how many photons you need per second.
Do you have a formula then? And
It's not a formula. I'm just saying each one is this much energy.
okay.
So how many do I need to make 4? You got that? Yeah?
Just a minute.
Yeah? Okay, continuing.
Yeah.
Right, so you have this other concept where photons are important. You probably know this maybe from chemistry, that we can picture on a metal surface that the electrons are trapped and they need energy to be freed. Have you done this in chemistry? It's a bit like ionization, you know, that you need to give something, first ionization, second ionization, you know this from chemistry, that you need to give it energy to be freed. You've done this in semester 1, I think. Yeah. Anyways, the same idea. We have electrons on a metal surface and they're trapped on the metal surface. They require energy to be freed. Therefore, they have a negative potential energy. The energy required to free the electron is called the work function. So the definition is the work function is the minimum energy needed to remove an electron from a solid to a point outside the solid. In other words, is the energy you need to free an electron from a metal surface.
The unit is well.
The unit is joules. Got that? Yeah? Yeah? So, when photons strike a metal surface, it can cause the release of electrons from the metal surface because the electron can get the energy from the photon when it strikes, when the photon strikes the electron. If and only if the photon has enough energy. So you have your electron that's trapped. If you have a photon with enough energy that hits this electron, it could free the electron. Just like in chemistry with your ionization. Similar idea. This is called the photoelectric effect. The photoelectric effect is freeing electrons by hitting them with photons. This is the photoelectric effect. Can you write this down? This is a definition as well. Yeah. You got this? Yeah? Continue? Continue? Yeah? Yes?
Energy.
When photons
No.
Right. Now let's have a look at this. So here's an example of photoelectric effect. You have a little battery here and a resistor. I mean, I guess it's not too important about these particular parts, but you have this glass case vacuum, and in it there are two metal plates. And what happens is, no, I don't need to write anything just yet. The sunlight comes in, and it hits this metal plate here. And what happens? The metal plate, hits this metal plate here. When the sunlight hits the metal plate, the photons of sunlight give energy to the electrons, and what happens to the electrons? They're freed. So the electrons then are freed, and they move around in a circuit here. So when there's more sunlight, or less sunlight, or whatever, there's going to be different behavior. So I want you to think about this. If there's a low frequency, that means the light is a kind of red colour, and low intensity, that means not much light, dim light. What do you think that means for the voltage? Is there many, or the current, the current. Are there many free electrons? Not many free electrons? What do you think that might mean? Yeah, well, if there's low frequency, that means they don't have much energy. And if there's low intensity, that means there's not many of them. So no surprise here that you only get some free electrons, but not many. And the electrons won't have much energy when they're freed. If you had high frequency and low intensity, so the light was quite high in its frequency, like a purple colour, but there wasn't much light, what do you think that would mean?
More electrons will be freed, but they will be very slow. So it seems like.
So high frequency would be more freed electrons. High frequency would be some free electrons of high kinetic energy. So, I mean, again, you have free electrons, but because the light is low intensity, what am I trying to say? The high frequency light will free the electrons, but because there's not many photons, there's not going to be many freed electrons. Actually, you know what, I think I might want to draw this on a plate here to show you. So, for example, where's my pen? Here we go. Yeah, I'll draw it here. So, here's our plate. So let's look at the first case where you have low frequency and low number of photons. So you don't have too many photons coming in, and they have a low frequency, so they won't free many electrons, and the electrons won't have much energy. But if this had a high frequency, it's still going to free the electron, but the electron will have more energy because the photon had more energy. Remember that the energy is conserved. What's happening is the energy from the photon is going into the electron. If this energy is big, because the frequency is big, then the electron, it will be freed and it will have lots of extra energy. But because there's not many photons, there won't be many freed electrons. So in this case here, you will have some electrons being freed, not many, but the ones that are freed will have a lot of energy. What about low frequency but many photons, high intensity, bright light? What do you think that will mean?
Low intensity.
No, high intensity,
But
low frequency.
some
Some of them will be freed, is it? No, many will be freed because you have many photons coming down. But because the frequency is quite low, when the electron is freed, it won't have much extra energy. So there'll be many freed electrons, but they'll have a low kinetic energy. And then the last one is high frequency and high intensity. So the high intensity means many will be freed, and the high frequency means the ones that are freed will have much more energy than they need. So it's many and high kinetic energy. I don't think you need to write this down, but I'm just trying to get you to understand what's happening here. Okay?
So, but basically, you mostly need high intensity.
It depends what you want to accomplish. Do you want your freed electrons to have lots of energy, or do you want lots of free electrons? Which is it, you know? So if you want lots of freed electrons, you should have lots of bright light. But if you want your electrons which are freed to have lots of energy, then you should have a high frequency. Because remember, energy equals HF. More frequency means more energy, which means more kinetic energy. So it depends what you're trying to accomplish. Do you understand?
Is this what is in solar panels?
Solar panels work like this, yep. Yep. Huh? No, it just means there's a different result. So for example, this one here, I suppose it doesn't really have, it only just has a different result for what you get at the end. Like, if you want lots of freed electrons, you need the light to be very bright, so there's lots of photons. But if you want the electron to be freed and have lots of energy when it's freed, then you need the light to have a high frequency. So it needs to be like a purple color or ultraviolet. That's all. I'm just trying to say that there's two features at play, the frequency and the intensity. That's all. Yeah. Now, I'll explain this formula. I had it here in the diagram. So if you look at an electron which is, maybe I should have done this first. If you look at an electron which is trapped on the plate, this electron here which is trapped, let's say it's not moving. What energy does this have? Does it have kinetic energy? No. Does it have potential energy? Yes. Negative potential energy. In fact, the energy here will be minus the work function. That's its potential energy. Okay? When you have a photon that comes along and hits the electron, what happens to the electron? It'll be freed. Yeah? Oh, come on. Don't do this now. Come on. Okay, so the electron will be freed. Here we go. So then the electron moves off here. What type of energy will the electron have? It'll have kinetic energy. And this photon here, what energy will it have? What's its formula for its energy? HF. So what energy do we have at the beginning? At the beginning, there are two things which have energy. What are they? The photon and the electron. How much energy does the photon have at the beginning? HF. How much energy does the electron have? Minus work function. After the photon hits the electron, the photon is gone and the electron is freed. What is the energy after the collision? KE. So this is a formula where you can relate the kinetic energy of the electron with the frequency and the work function. So if the frequency is bigger, then the kinetic energy will be bigger. If the work function is bigger, what happens to the kinetic energy? Work function is bigger, will be lower. So if this metal has a bigger work function, the result is the freed electron will have less kinetic energy. So you can draw this diagram, I think you should, and also this is the formula. Or you can rearrange it normally as HF equals work function plus kinetic energy. So we can rewrite that as HF equals work function plus kinetic energy. Okay, can you write, so draw that. Yeah. You drew that?
Yeah.
Yeah, continue. So this formula is important. Okay. Right, so let's have a look at an example. You have a piece of copper. Its work function is 4.7 electron volts. A photon of this wavelength strikes the metal surface. After the photon strikes the metal surface, an electron is freed and travels at a speed of v. What is the work function in joules, and what is the speed of the electron? So I'll draw that for you as well. What's happening here? Well, you know what? Why don't you try it first? Because I think you should be able to do it. Because you have the formula there.
We will have to change electron volts to volts.
Question 1. What is the work function in joules? Try this.
Very big or very small?
Very small, I think, yes. Okay, let's start doing this together. So you had a chance to think about it. What you have is you have your metal plate, and it has a work function of 4.9 electron volts, was it?
Yeah.
Shivers, KJ. Did you get a pair of glasses?
No, I wrote 7 here.
Alright. 4.7 electron volts. So in joules, that is...
246 and 10 power minus 11.
Okay. No. It's 7.5 times 10 to the minus 19 joules. We did this already, didn't we?
Yeah, I know we did it, but like when I did it, it's getting...
I just multiplied 4.7 by E on the calculator.
What's the...
E 1.6 times 10 to the minus 9.
But why did you multiply it?
Oh my goodness, you're forgetting stuff we did. We did this in electric fields. We use electron volts as a different unit to joules.
Yes, 1 joule is equals to 1 E. 1.6 times 10 to minus 19. So 4.7 electron volts will be equals to how many joules?
Okay. 1 eV of energy is the same as 1.6 times 10 to the minus 19 joules of energy. I have 4.7 EVs, so I multiply this by 4.7. Right, so that's the A part. Now the B part. You have your photon of light. What's its wavelength? 500, 550 nanometers. So the photon comes in, it hits the electron is freed. The formula, what's the formula for kinetic energy? Or what's the formula I gave you? HF equals work function plus kinetic energy. So kinetic energy, HF minus work function. What's the formula for F? Well, you remember you have C equals F lambda, so what does F equal?
Lambda over...
Try again.
Over
Alright, so do you know H? Yes. C? Yes. Wavelength? Yes. And work function? Yes, now you do. Right, what's the H?
6.7 times
6 point...
6.626.
It's okay, I got it on the calculator. H times C over lambda
H times C, yes.
minus 7.5 times 10 to the power of minus 19. So you have the kinetic energy is equal to, hang on, it shouldn't be negative. Did I write the formula down wrong? HF equals, I wrote the form, I have it backwards, sorry. The formula was HF equals work function plus kinetic energy. Oh no, I wrote that right. HF minus work function. And then what did I type in wrong? Did you get a negative answer as well?
Yes.
I did something stupid. HF minus work function 0 lambda.
HF minus work function. Is that's correct?
Yeah. So why did I get a negative answer? Unless I put in the wrong numbers. Maybe...
Yeah.
No, maybe my work function is too big. See if I make it smaller. Yeah, I think I made the work function here too big for this problem. Instead of 4.7 electron volts, let's make it something smaller. Oh, it is, yeah. We'll make it... Did I say this was copper, was it? Okay, do you know what I'll do? I'll just make the light a smaller wavelength. Yeah, okay. Right, can you just change in the question the wavelength to 250 nanometers?
Wavelength to 250.
Yeah.
So was it the wavelength that was the problem of the law?
The wavelength, the light wasn't strong enough to free the electron. So the kinetic energy is 4.5 times 10 to the minus 20 joules. Now, how can I get the speed of the electron? A half mv squared equals 4.5 times 10 to the minus 20. So the v will equal 4.5 times 10 to the minus 20 times 2 divided by the mass square root. Now the mass is on the calculator as constant number 3.
So the mass of the
Electron, yeah. That seems like a good answer. V equals 314,771 meters per second. Or 314 kilometers per second. Yeah, okay. Let me just, so I don't forget, let me fix that. What did I go with? 250, wasn't it? Yeah, okay. So next now. So your work function means the electron has E equals minus phi, minus work function at the beginning. In order to free the electron, it needs this much energy. If it gets more than this energy, then it has kinetic energy. But yeah, this is where it gets threshold. So let me explain it here actually. So look, what you would like now how much energy does this electron have on the metal plate? Minus the work function. Yeah? Mm-hmm. You have your light. How much energy does the light have? HF. And what you want is you want the electron to be freed, but you don't really want the electron to move. You just want it to be freed. Just about freed. Just barely freed. So what's the kinetic energy here? If it's not really moving? 0. So remember your formula was HF equals work function. So if the kinetic energy is nearly 0, then you could say F equals work function over H. This is the frequency to just about free the electron. And actually this frequency is called the threshold frequency, F0. It's the frequency which just about frees the electron. So what happens if the light has a frequency less than this? Yeah, it's not free. Continue. Yeah. So this is called the threshold frequency. Can you make note of that word, threshold frequency? Yeah? Okay. Yeah? Correct?
Yes.
Yeah. Okay, let's have a look at an example. So, can you calculate for me, please? Gold, this metal, has a work function of 5.1 electron volts. What is the threshold frequency?
We have to change it to blue.
What do you think K to the J?
We don't need.
Yes, you do. Jules.
Because
I doesn't. You need to convert it. I don't need to ask you to do that. I just did that last time to be nice.
Uh, 1.23 times 10 to the 15. So let's see.
1.23 times 10 to the 315.
Yes. So we could say maybe 123 times 10 to the 13.
Yeah, so the answer is 1.2 times 10 to the 15 hertz.
but do we have H?
It's a constant.
Oh, sure.
We won't bother with the B part. Okay. Did you get that?
Yeah, I got it.
Right, okay. Can you take a note of this, please? Snap, snap.
Yeah, no,
I will upload it later, yeah. Okay, you got this?
Okay.
Great, okay. So, really there's only really one formula or two formulas for this lesson. The energy of a photon, which is HF, and then the work function and the threshold frequency. Okay, let's have a look at the next topic. Yeah. Photosystem is, you might have heard of it in biology as like photosynthesis. Just a photosystem is like a solar panel but for plants. A way to get energy from the light.
Changing carbon dioxide.
No, we won't, not as complicated as that. We just care about the process of taking the energy from the light. Think of a photosystem as a natural solar panel. You know solar panel? Yeah. So a natural solar panel of a leaf.